Hello, everyone. So I'm glad to introduce the speaker of today, Amir Fernández Ouaridi, who's going to talk on, let's see, on the simple transposed Poisson algebras and Jordan superalgebras. Please, would you make your presentation full screen?
Yes. Am I sharing the screen? Yes.
Yes, but I'm not sure if it's well, for me, it shows only part of your screen. I mean, it's too big that my screen can only view of it. Maybe it's a problem with the configuration.
No, it is full screen.
It was okay, yes.
Okay, so it's maybe a problem of mine.
Okay, so thank you very much for the invitation. I'm going to talk about simple transposed Poisson algebras and Jordan superalgebras, as you have said. I have structured my talk in 3 parts. In the first part, I'm going to introduce some definitions and relations with other classes. In the second part, I'm going to talk about the Kantor double of a transposed Poisson algebra as a first possible idea to classify simple transposed Poisson algebras. And in the third part, I'm going to talk about simple transposed Poisson algebras and some of the main results of the talk will be there. Okay, so first, I'm going to start by giving the definition of a Poisson algebra, which is a vector space endowed with 2 multiplications, one being associative and commutative, and the second one being a Lie bracket. And for these 2 operations, we will require to satisfy an additional identity involving the 2 multiplications, which is usually called the Leibniz rule, which is this one here. The first historical encounter with Poisson algebras is in Hamiltonian mechanics in the 19th century, where the algebra of smooth functions on variables the space of coordinates and their corresponding momenta is endowed with a Lie bracket, which satisfies the Leibniz compatibility rule. And this bracket is given by this product here, this sum here. Okay. Now, the study of Poisson algebras has led to the study of various related Poisson-type algebraic structures, including generic Poisson algebras, algebras of Jordan brackets, contact brackets, Novikov Poisson algebras, and many others. And in a paper of 2020, that appeared in 2020 in Archive, a dual class of Poisson algebras, or the class of Poisson algebras, was introduced, and these are the transposed Poisson algebras. This class was introduced by changing the roles of the 2 multiplication in the Leibniz rule. Okay, so fixed a field of characteristics different from 2. A transposed Poisson algebra is a vector space P with 2 multiplications, one being associative and commutative again, and the other one being a Lie bracket. And the compatibility rule, instead of being the classical Leibniz rule, it is this identity here, which is called the transposed Leibniz rule, which, as you can see, we have changed the roles of the 2 multiplication. If you see in the Poisson case, we have that the Lie bracket, the left multiplication, the right multiplication in the Lie bracket is a derivation of the associative commutative multiplication. And in the case of transposed Poisson algebras, the associative commutative multiplication is the one that is a derivation of the Lie bracket, except for this term, these two here that appear here, that I will explain later why it is here. Okay. So in this talk, we will assume that the Lie bracket is not abelian in general for any transposed Poisson algebra. Let me comment some examples. If we have an associative commutative algebra with a derivation D, we can define a new product in A given by this bracket here. Then this construction, the circle and the bracket, will be a transposed Poisson algebra, and these transposed Poisson algebras can be called transposed Poisson algebras of vector type. Okay, a contact bracket is a vector space P with an associative commutative multiplication with a derivation, and an associated Lie bracket satisfying this identity, which generalizes the Leibniz rule of the Poisson algebra. So contact brackets are generalization of the Poisson algebras, and any Poisson algebra is a contact bracket if we take the derivation to be 0. Now, in this paper by Beites, Ferreira, and Kaigodorov, they show that unital transposed Poisson algebras are contact brackets, and also unital transposed Poisson algebras are of vector type by choosing D, the derivation D, to be the multiplication by the unit. Okay, the multiplication of the Lie bracket by the unit. Another example, this one is also very interesting, is if we take the field to be the complex field, then the Lie algebra of derivations of the algebra of Laurent polynomials is the Witt algebra, which we will denote W. The Witt algebra is defined on the vector space generated by the elements AI for I in Z, and endowed with the product given here. And then if we define a mutation of an algebra P, of an associative commutative algebra P, to be by an element Q, to be a new algebra, where we have defined a new product in this way, then what was proved by Ferreira, Kaigodorov, and Lopatkin in this paper here was that any transposed Poisson algebra constructed on the Witt algebra has associative commutative part isomorphic to a mutation of the algebra of Laurent polynomials. And also none of these algebras is Poisson algebras. So for transposed, another example of a transposed Poisson algebra will be the Witt algebra together with an algebra isomorphic to the algebra of Laurent polynomials. Okay. Now, how do they prove this result? Well, what they do is that they introduce, they don't introduce it, but they use the notion of a 1/2 derivation of a non-associative algebra. Okay, and a 1/2 derivation of a non-associative algebra is a linear map D, which satisfies this equation here. In general, if we choose phi, a map phi of this form, where alpha is an element in the field, is always 1/2 derivations. So these kind of maps are usually called trivial 1/2 derivations. Then we can see that the transposed Leibniz rule can be realized as the left multiplication of the associative commutative algebra to be a 1/2 derivation of the Lie bracket. Okay. Also related with 1/2 derivation, they have been they are well studied. For example, by Filipov in this paper here, delta derivation for Lie algebras. And one of the main results in this paper is the following. If we have a prime Lie algebra over a field of characteristic different from 2 and 3, endowed with an undegenerate symmetric invariant bilinear form, then if we denote the centroid of the algebra by gamma of L, then we have that gamma of L is equal to the one-half derivations of L. Okay. In particular, for finite-dimensional complex simple algebras, we can choose this bilinear form to be the killing form. So we have that the derivations will coincide with the centroid, and it is easy to see that the centroid is isomorphic to C. So basically, any one-half derivation will be trivial. That is a map of this type. Okay. Now, using this idea of this idea of the one-half derivation that was used in for the previous theorem, other examples of transposed Poisson algebras were constructors on other particular families of Lie algebras over the complex field. For example, a selection of these papers are the following. We have the algebraic and geometric classification of transposed Poisson algebras of dimension 3. We have the transposed Poisson structures on the block Lie algebras. We have the transposed Poisson structures on the Galilean algebras, on the Witt type algebras, on the Lie algebras of upper triangular matrices, and on the generalized Witt algebras and block Lie algebras. Okay, so there are many examples. Now I'm gonna mention some relations with other classes of algebras. The first relation I want to mention is with Novikov Poisson algebras. A Novikov Poisson algebras is a vector space P equipped with two bilinear operations, an associative commutative multiplication, and a Novikov multiplication, satisfying these two compatibility rules. Okay. Then, what was proved by Bai and other three authors was that if we take the commutator of the Novikov part in a Novikov Poisson algebra, we obtain a transposed Poisson algebra. Also, there is a relation with Helfand-Dorfman algebras. A Helfand-Dorfman algebra is a vector space with two bilinear multiplications, a Novikov algebra and a Lie algebra, with this additional compatibility rule. The variety of Sartayev in this paper here proved that the variety of transposed Poisson algebras coincides with the variety of commutative Helfand-Dorfman algebras, and he also proved in this paper that transposed Poisson algebras satisfy all the special, well, Helfand-Dorfman algebra is called special if it can be embedded into some Poisson algebra with a derivation. Through the map, this one here. So what Sartayev did in this paper was that he showed that the transposed Poisson algebras satisfy all the special identities for the special GD algebras up to degree 4. So he conjectured that any transposed Poisson algebra is special, but we don't know if this is true. Okay. There is also a relation with another class of algebras, which are called the weak-Leibniz algebra. A weak-Leibniz algebra is an algebra satisfying these two identities here. As one can imagine by the name, any Leibniz algebra is a weak-Leibniz algebra. This class was introduced by Suma Dildaev in this paper here. And look, if we have a transposed Poisson algebra, we can consider a new multiplication dot by taking the sum of the two multiplications, taking first the circle and summing it to the bracket, and this new algebra dot is called the polarization of P. Conversely, if we have a weak length algebra, we can consider two multiplications, circle and bracket, defined in this way here. And this new algebra is called a polarization of L. What Sumadildaev proved in this paper was that any depolarized transposed Poisson algebra is a weak length algebra, and any polarized weak length algebra is a transposed Poisson algebra. Okay. Now, the last thing I'm going to introduce is the definition of a transposed Poisson superalgebra. It is defined as one can expect. We will have two multiplication, an associative supercommutative multiplication and a Lie superalgebra multiplication. And additionally, we will have two operations. We will have that these two operations satisfy this compatibility rule that we have here. Okay. Some examples and some results of transposed Poisson superalgebras were studied in these two papers here below. Okay. On the topic of as you can expect, we can also define some kind of super derivation, and we will have that the associative supercommutative multiplication will be a 1/2 super derivation of the Lie superalgebra multiplication. Okay, so look, in a paper by Kaykodorov, it was proved that the space of 1/2 derivations of a finite-dimensional simple Lie superalgebras over an algebraically closed field of characteristics 0 are trivial. And this result was later generalized by Susmanovich in this paper here, where he proved that the space of 1/2 derivation of a perfect centerless Lie superalgebra over a field of characteristics different from 2 or 3, having a non-degenerate supersymmetric invariant bilinear form, coincides with the centroid. And this result here will be important later in the talk. Okay. Now, now I'm going to talk about the Kantor table of a transposed Poisson algebra. Okay, so first, an ideal of the algebra is a subspace I that is simultaneously an ideal in both multiplications. The algebra with no ideals is called simple. Okay, it was proved by Kantor that any non-trivial simple finite-dimensional Poisson algebra over an algebraically closed field of characteristics 0 was isomorphic to one of the algebras of the family Hn. This family is sometimes referred to as the Grassmann-Poisson algebra. Okay, and I'm not gonna give the definition of this algebra, but you can find it in the paper. The interesting part of this theorem is the way he uses to prove it. Okay, so first, Katz used the classification of simple Lie superalgebras and the TKK functor for Jordan superalgebras in order to classify all the simple finite-dimensional Jordan superalgebras over an algebraically closed field of characteristics 0. Kantor then introduced an invertible way to construct a Jordan superalgebra from a Poisson algebra, the Kantor table. This construction presents this simplicity in both directions, so a classification of the simple finite-dimensional Poisson algebra over an algebraically closed field of characteristics 0 was obtained. As a curiosity, the Jordan superalgebra corresponding to Hn through this construction was omitted in Katz's classification, apparently because one of the possible gradings was omitted. Okay. Now, what is this construction? If we suppose F is an arbitrary field of characteristic different from 2, the Kantor double in the most general context, which is for an algebra P, for a superalgebra P with two multiplications, circle and bracket, the first multiplication being associative and supercommutative, and the second one being super-skew symmetric. This class is usually called dot bracket superalgebras, by the way, and this construction is the following. If we denote by PS a duplication of the space P with opposite parity of the elements, so if we have an element X in Pi, its corresponding copy XS will have parity I plus 1, then JP will be the vector space P plus the copy of P, endowed with a multiplication star given for homogeneous elements, given for two homogeneous elements by these products here. So X star Y will be the circle of XY, X copy star Y copy will be the bracket of XY with this sign here. When we multiply one element in the copy and one element in P, then we will take the circle and then take the copy of the element that we obtain by the circle. By this construction, the algebra JP is a superalgebra with even space. This one here, P0 plus P1s, and other space P1 plus P0s. And look, this JP will have double the dimension of P, and hence is named the Kantor double of P. Okay, so there are other reasons why the Kantor double is important. It's not just important in the proof of Kantor of the classification of the simple Poisson algebras over an algebraically closed field of characteristics 0. This construction is also important because one of the most important families of infinite-dimensional simple Jordan superalgebras is precisely the family of those superalgebras that are obtained by the Kantor double of some contact bracket. They also appear in the description. This construction also appears in the description of the simple Jordan superalgebras in positive characteristic. One of the main families in particular are constructed through the Kantor double of some the algebras, which are called the Jordan brackets, and also in the particular context that we are talking about, if we take Sakharov showed that if we take the commutator of a Novikov-Poisson algebra, which we know it is a transposed Poisson algebra, we can see that the commutator of a Novikov-Poisson algebra is a Jordan bracket. Okay, so a Jordan bracket is the algebra which, when we apply the Kantor double, we obtain a Jordan superalgebra. Okay. Okay, so now the last definition I want to introduce is the following. A quasi-ideal of a transposed Poisson algebra is a proper subspace I of P such that I is an ideal of the associative commutative algebra, and we have that P bracket I multiplied by P is contained in I, and also another definition is the transposed version of this definition. A transposed quasi-ideal is a proper subspace I such that we have that it is an ideal of the Lie bracket, and we have that Pi bracket P is contained in I. Okay. Then what we can prove is that if P is a transposed Poisson algebra, then the algebra JP, which is the which it denotes the Cantor double of P, is a Jordan superalgebra. Okay. As a remark, we can see that if P has an ideal I, then its Cantor double has an ideal I plus I copy. Therefore, if JP is simple, then P must be simple. Moreover, if P is a simple transposed Poisson algebra, which has not a perfect associative commutative part, then this sum here will be an ideal of the Jordan of the Cantor double of P. Hence, if the Cantor double of P is simple, then P is simple, and the associative commutative part must be perfect. And the converse is also true. And to prove it, we first prove that in any simple transposed Poisson superalgebra with perfect associative commutative part, we cannot find quasi-ideals. And using this lemma, we can prove that the simplicity criterion, which is the following. If P is a simple transposed Poisson superalgebra such that P times P is equal to P, then JP is simple, and the converse is also true, as we have mentioned in the previous slide in the remark. And also, as a remark, there is no simple finite-dimensional transposed Poisson superalgebra with perfect associative commutative product over an algebraically closed field of characteristic 0. And how do we know this? We know this just by looking at the classification of the simple Jordan superalgebras over an algebraically closed field of characteristic 0 that was given by Katz. Okay, but this is but what happens with the simple ones that do not have perfect associative commutative product? We don't know. We also wanted to investigate whether it was possible to obtain a simple Jordan superalgebra from a non-unital transposed Poisson algebra. And look at this example. If we fix an element Q in the Witt algebra, we can denote by PQW the transposed Poisson algebra consisting on the Witt algebra with the mutation of the Laurent polynomials corresponding to the element Q. Then the Cantor double will be given by the following multiplication here. What we can see from this algebra is that the associative commutative part of PQW is perfect if and only if it is unital. So this algebra, JPQW, are simple if and only if Q is invertible in L. In fact, what we can see is that they have to be unital to give rise to a simple Jordan superalgebra. If we let me recall a definition. An algebra is differentiably simple for a family of derivations D if it is non-trivial and it contains no the invariants ideals. We say an algebra is differentiably simple if this is true for some family of derivation. And Posner showed that differentiably simple associative commutative algebras are unital. So using this fact, we prove that if we have a simple transposed Poisson superalgebra such that P times P is equal to P, then the associative commutative part is differentiably simple and therefore unital. So P will be a contact bracket and of vector type. In other words, we will only obtain simple Jordan superalgebras if we start with a a transposed Poisson algebra, which is a contact bracket, and it is of or it is of vector type. Okay. Also, for this algebra of this algebra we have defined, this Jordan algebra that we have defined in the previous slide, we can see that, look, Macrimon showed that unital associative commutative algebras with a derivation together with the bracket, with this bracket, produce special Jordan superalgebras when considered the Kantor double. So it follows that if Q is an invertible Laurent polynomial, then the algebra we have previously defined is special. So this question is very natural. Is there any exceptional Jordan superalgebra arising from the Kantor double of transposed Poisson algebras? I leave it here. Now, we can also define another construction very similar to the Kantor double, which I called the transposed Kantor double, in the following way. It was also introduced by Kantor. It also appeared in the paper by Kantor, and he defines this construction in the following way. He takes two elements in P and their corresponding copies in PS and set the multiplication star T to be exactly the transpose of what he does in the normal double. He takes the product of two elements in P to be the bracket and the products of two elements in the copy to be the circle. And when he takes one element in the copy and one element in P, then he uses first the bracket and then applies the S. So in the case of Poisson algebras, this construction gives a Lie superalgebra. In the case of transposed Poisson algebra, this construction does not give a Lie superalgebra. So is it any interesting class of superalgebras? I don't know. This is another question I leave here. So now for simple transposed Poisson algebras, let me first give a note on the existence of transposed Poisson structure. A dot-Lie bracket is an algebra, is a the algebra such that the dot or the circle is an associative commutative algebra and the bracket is a Lie algebra. For a dot-Lie bracket, Witt et al. Proved that Poisson algebras, if this the algebra is a Poisson algebra and a transposed Poisson algebra, if and only if this identity here is satisfied. However, we have to mention that this identity here, which you can see that it doesn't have the equal to 0, implies already that it will be equal to 0. So we have collected this fact and some other equivalent statements in the following proposition. If we have a dot-Lie bracket, then the algebra P is a transposed Poisson algebra and a Poisson algebra if and only if the identity of Witt et al. Is satisfied, if and only if this identity here without the 0 is satisfied, if and only if we have Px, which is the linear operator of length multiplication of the associative commutative circle, is in the central for any element in the algebra. Okay. As a corollary of this proposition, we have that a Lie algebra with a centroid equal to the space of one-half derivations then for a Lie algebra, so that the centroid coincide with the space of one-half derivation, then any transposed Poisson structures on L is also a Poisson algebra. On the contrary, if the centroid is isomorphic to the field, then any non-trivial transposed Poisson structures on L is not a Poisson algebra. Also, if we have a Lie algebra with this property, the centroid coinciding with the one-half derivations, then L admits a non-trivial transposed Poisson structure if and only the center of L is different from 0 and L is not perfect. In particular, complex simple algebras do not admit any non-trivial transposed Poisson structure. Okay. Also, as a corollary, which is obtained also using the result by Filipov, is the following. If we have a prime Lie algebra over a field of characteristic P with a non-degenerate symmetric invariant bilinear form, then L do not admit a non-trivial transposed Poisson structure. Okay. Now, for simple transposed Poisson algebras, if we are over a field of characteristic P different from 2, we can prove the following. We can prove the following result. Look, theorem 47. A transposed Poisson algebra is simple if and only if the Lie bracket is simple. So all we have to look at, if we want to know if a transposed Poisson algebra is simple, is to look at the Lie bracket. And how do we prove it? We prove it in 3 steps. In the first step, we prove this lemma that says that in any simple transposed Poisson algebra, the Lie bracket must be perfect. Then we prove that a simple transposed Poisson algebra contains no transposed quasi-ideals. Then we prove that a transposed Poisson algebra with the associated Lie bracket being perfect, then any ideal in the Lie algebra is a transposed quasi-ideal. So using these 3 steps, we obtain the theorem 47. Okay. Now, as a consequence of this theorem, we have the following result. Any simple finite-dimensional transposed Poisson algebra is trivial. Also, by this result, if you remember, I defined these weak-length algebras. For weak-length algebras, we can also prove that the simple finite-dimensional ones are either associative commutative algebras or Lie algebras. And this is because the simplicity is preserved by the process of polarization and depolarization. So since every simple finite-dimensional transposed Poisson algebra is trivial, then it follows that any weak-length algebra must be either a associative commutative algebra or a Lie algebra. Okay. Another consequence is the following corollary. A non-trivial transposed Poisson structure defined on a simple associative commutative algebra has simple associated Lie bracket. This is obvious, but look, is there any non-trivial transposed Poisson structure with simple associative part? Yes, there is one example which was found by Suma Deldaev, which is the following. We have to take as the associative commutative part the field of formal series in one variable and some formal derivation in there, and then define the bracket to be of this form that we already know that If we take the bracket in this form, it will be a transposed Poisson algebra. And now by the previous corollary, this Lie bracket will be simple since it is clearly not zero. Okay. Now, another consequences is the following theorem. If we have a transposed Poisson algebra, the associated Lie bracket is a direct sum of simple ideals if and only if the transposed Poisson algebra P is a direct sum of simple ideals. In an algebraically closed field of characteristics 0, finite-dimensional semi-simple Lie algebras are precisely those that can be written as a direct sum of simple ideals. And also, semi-simple Lie algebras have no non-trivial one-half derivations. So we have the following corollary. If F is an algebraically closed field of characteristics 0, and P is a finite-dimensional transposed Poisson algebra, which is a direct sum of simple ideals, then it is trivial. In the case of transposed Poisson superalgebras, we can pretty much do the same. Recall that a graded ideal in a transposed Poisson superalgebra will be a graded vector space with it is an ideal for both multiplications. Then a superalgebra will be called simple if it contains not graded ideals. A graded transposed quasi-ideal of a transposed Poisson superalgebra is a graded proper subspace satisfying, again, the two properties that we had before, but for the graded idea. Then what we can prove using this definition is that any simple transposed Poisson superalgebra has simple super Lie bracket. By a similar argument as in the case of Poisson algebras, but using the fact that simple finite-dimensional Lie superalgebras have no non-trivial transposed Poisson superalgebra structure, we can conclude that over a field of algebraically closed field of characteristics 0, any simple finite-dimensional transposed Poisson superalgebra is trivial. Now, what happens in the case when instead of one of the multiplications being simple, we want it to be just perfect? Well, if we fix F to be an algebraically closed field of characteristics 0, and we denote the descending derivative series of an ideal I as this bracket of K, the next result follows. If we have finite-dimensional transposed Poisson algebra, and we denote by R the radical of the associated Lie algebra, then Ri is a not necessarily proper ideal of the transposed Poisson algebra P for any I. And the following question is natural. Is the radical of the Lie algebra an ideal of the transposed Poisson algebra in any field? I don't know. If we have now a finite-dimensional transposed Poisson algebra with perfect associative commutative multiplication, then the associated Lie algebra must be solvable. And this is a consequence of the theorem above. In particular, if the associative commutative algebra is unita, then the associated Lie algebra is solvable. Okay. On the other hand, if the Lie part is perfect, we have the following. If we have a finite-dimensional transposed Poisson algebra with perfect Lie part, then the associative commutative algebra is nilpotent. Okay. Now, let's talk about some examples of finite-dimensional simple transposed Poisson algebras, which can be found in the case of fields of positive characteristics. So we want to show that there are non-trivial simple finite-dimensional transposed Poisson algebras in characteristic P for P greater than 3. And we have to recall the definition of a modular Witt algebra. If AP is the truncated polynomial algebra in one variable, where this is denoting the ideal generated by XP, and F is a field of characteristic P, then the modular Witt algebra WP is the Lie algebra of derivations of AP. And it is well known that WP is simple for P greater than 2 and that it has a basis of these elements such that the multiplication is given by this bracket here. By assuming that if EK is EK will be 0 if K is less than minus 1 or bigger than P minus 2. Moreover, note that SL2 coincides with the modular Witt algebra in characteristic P equals 3. So it coincides with W3. Well, what we can prove is that if WP circle bracket is a transposed Poisson structure on the modular Witt algebra WP with P greater or equal to 3, then the algebra WP is isomorphic to a mutation of the algebra of truncated polynomials in one variable, AP. And conversely, any mutation of AP endows WP with a transposed Poisson algebra structure. And moreover, none of these algebras is a Poisson algebra. So, so this theorem gives us an example of a finite-dimensional simple transposed Poisson algebra for any characteristic. Okay, and motivates the following question, which is to classify simple finite-dimensional transposed Poisson algebras in positive characteristic. And this this talk is based in this paper, and these are some references. Thank you.
Thank you very much. Other questions? I have seen there are questions in the chat, but
okay, let me read.
I have to refer to them. Probably 49.
Okay. Hi. What can be? What can be said about the intersection of the two classes of algebras obtained in the conclusion of the corollary? I'm not sure if I understand the question, but
the intersection of social cognitive and Lie algebras.
That's the question.
Is it the question?
There is no intersection. The intersection is the abelian algebra.
well, over the field of characteristic 2.
No, but he's not saying over the
It
field
is
of
not-
characteristic 2.
I mean, commutative and anti-commutative is the same, and associative implies leading. But okay, P equals 0 here, so it's not the case. Yeah, so only the trivial algebra. And then there is another question.
Can you
Can
read
give
the
the
references
references?
slide? Oh. And anyone in particular?
Yes.
Algebra, which is also associative algebra. I don't know. Well, if you have a Lie algebra which is an associative algebra, it won't be commutative. So
yeah, commutative and anti-commutative over a field of characteristic 0 implies that the product is 0. And independently of the Jacobi identity, I guess.
now Janice is asking for the references. Do you want to see any page in particular? Okay.
So, Yanis, are you interested in some particular reference on this list?
This is the paper where you can find all the results I have talked about. Okay.
So it's already published.
Yes,
Accepted.
it's published.
Yeah, I remember that there was some discussions during the workshop in Oberwolfach. So I remember the discussions in Oberwolfach, those questions that Askar asked. And do you have some update on that topic?
No. No.
Okay, so everything that you have told today is published in that paper. Nothing new since Oberwolfach.
Well, there is something new, and there is also something new in the paper, which was not in the workshop, but yes.
Okay, so more questions? All right. So, okay. Thank you for the talk. Thank you for, and I thank all the participants for their presence. So, have a nice week. And see you next Monday. Bye bye.
Bye.